suppose we have y equals to f of x, some function. And we're also given an interval a to b. Now, so far, we've been talking about areas and volumes. This time, we're not going to be talking about areas, but rather the length between these two points. How do you find that curve length? That's the question. How do you find this length?
What does it have to do with Simpson? What Simpson's rule? Right sum, left sum,
No.
chop sum?
We can make it to involve Simpson's rule and all that, but at this point, no. So we're going to use small s for this length, which is very customary. For arc length, people like to use s, sometimes L. And we want to know what s is. How do you find any quantity using an interval? What's like the universal rule?
b minus a.
No, that's for like finding interval. How do you find any quantity using interval?
It's the sum of all of its parts, all of the little tiny changes.
Yeah. So the whole is sum of its parts. That's the
Yes.
formula. And what should I write?
Integral of
Integral ds. That's what we always do. It's universal. Even in physics books, especially when you get to physics 2, you're going to see this in action a lot. Right? Okay, but what do I mean by ds, right? Anytime we write this, the whole is the sum of parts, you have to give meaning to this. It's not a formula you can calculate. You actually have to figure out what this ds means. And it actually depends on how you chop it off into small parts. The way I'm going to chop off this arc as well, actually, is because it's a one-dimensional thing, there's only one way to chop it off, like that. Right, just like that. Small parts. Now, what we're going to assume is that the graph of this function is somewhat smooth. And being smooth means that if you chop it into very, very tiny pieces and you magnify, you zoom in, you'll start seeing straight lines. Okay. Now, that's not true for some really weird functions. So, have you ever heard of fractals? Yeah, if you search them up, you see some geometric shapes that is not very smooth at all. So one example is something called a Koch curve. And it goes like this. You start with this one generation. Don't write this one, by the way. It's just a little thing I just throwing in. It's not the main lecture, okay? But what does Koch curve do? Well, you start with this one, and then you divide 1/3 of it, and you put the same kind of picture that you started with. And then for each of these small lines, you again delete 1/3 of it, and then you put like this one, and then this one, this one. Like, looks like a part of a snowflake. If you like put these, another one here, all around, you're going to get a snowflake. Now, if you have a graph like that, what's happening is that if you zoom in, this portion, it will look like the entire thing, right? So if you zoom in more and more, you will never reach a straight line. However, if you have a smoothly varying one, if you take this one and zoom in, it looks more like that one. And if you zoom this one, it's more like a straight line. And eventually, it looks like a straight line. Okay? And that's the beauty of it. Okay? So what we're trying to describe here is not going to be applicable for curves that are rapidly changing like this one, it doesn't work. It has to be differentiable, okay? Like this one. Okay, so what was I trying to say? Yeah. The beauty of it is that once you chop it up into small pieces, then the geometric object looks really simple. And that's what makes all of such arguments work. So when you recall what we did with the areas, we divided into very thin strips, and they started looking like a rectangle, right? For the volumes, when we took an object of revolution and chopped it into certain directions, they became like washers with like very small thickness, and they almost look like a cylinder. And then we use that to our advantage to calculate and then add them up to get the volume, right? Same idea here. If you chop it up into small pieces, then suddenly they look like a straight line, and this is our piece of ds. And now we have to figure out how to rewrite this into other things that you know. Notably, we can never do any integral with ds. We can only integrate by dx or dy, right? Okay. Yeah. So think about the following. I need to rewrite this as something times dx. Or maybe dy. What would this be? This would be ds over dx. Isn't that right? Yeah, okay. In this picture, what is dx?
In between A and B.
In those 2 points, no, not this entire thing. We've zoomed in just one portion. It's not the entire A and B, but it's this. This is supposed to be really, really tiny. Okay?
Oh.
So this length is dx. How about this length? It'll be dy, right? Oh, but then because we have a simplified picture, what does this look like?
A triangle.
A right triangle, right? And we can actually apply what formula? Huh?
D squared.
Yeah, we can say ds squared is dx squared plus dy squared, the Pythagorean theorem. And you can take the square root and say this. Okay. Now, although we can put this in here, it looks very cryptic. I've never seen such an integral, right? Yeah. However, if we use this, then it somewhat makes sense. See, we have so as long as I can make sense out of this, I just have to integrate by x. That's all it means. Okay? Then this one we have to work on it a little bit, and we'll be just using some algebra. Algebra can sometimes feel like sorcery, but it works. Yeah.
Professor.
Yeah.
Do you have to do dx? Or like
Oh,
dy?
that's a great question. So the question was, do we have to do dx? And the answer is no. Sometimes it's actually doable only if you do dy. So there will be another formula for dy and another for dx. Okay. So I'm just showing you what it looks like for if you pull out a dx, but I'll show you what happens when you pull out a dy instead. Okay. All right. So you have dx squared, and then I'm going to put this dx inside the square root by squaring it. And then you remember this thing, the heart-shaped?
Share the love.
Yeah, share the love. So we rewrite like that, so it's an integral of dx squared over dx squared plus dy squared over dx squared dx. And then what is this?
If it's one.
just the 1. Anything divided by itself is just 1, right? So integral of square root of 1. And we can rewrite this as dy over dx squared dx. Yes?
So how did you all of a sudden square the dx on the bottom? Can you?
The question is, how did this become square? Well, it was outside the square root. So I'm trying to rewrite this as, you can rewrite dx as square root of dx squared.
I see. Okay, you're trying to include
Yeah,
it
and
in the
then
whole
because
thing.
they both have square root, I can put just a single square root
Okay.
for the entire thing.
Okay, got it. Thank you.
Okay, now look at this formula. I've seen dy dx before. What's that called? What is dy dx?
The tan.
No.
No, that's.
Rate of change?
It's a rate of change. There's a name for it. What is this?
Slope.
Okay, slope, rate of change, they all mean derivative, right?
Oh.
Yeah, this is the derivative, right? Yeah. dy dx is just another way to write down f prime of x, right? So you know this, right? F prime of x is same thing as dy dx. Just two different notations for the same thing. Newton invented this notation, whereas Leibniz, the second founder of calculus, used this notation. Okay? The power of this notation is that sometimes it gets you to places where you wouldn't have known before, just by doing algebra. The power of this one is that it looks simple, but sometimes having just this formula would lead to blind spots that you wouldn't know what to do. So it's good to have both symbols. Okay? So this is really integral of square root of 1 plus f prime of x squared dx. And that's our formula. This is the arc length formula. Now I promised you that I'll tell you what happens if you divide by dy instead. In that case, it'll be, this will be dy and that will be dy, so that this over this will be 1. And this side will be dx over dy, squared.
So then what's that equal to?
Well, in this case, you're assuming
just
that
the derivative.
x is a function of y. So sometimes if you have a curve described as x equals to f of y, we had some example like that before, right? Some curve like that one. In that case, if you wanted to know this arc length, and it's given as x equals to f of y, then you'll be using this formula. Okay?
Unless you change it.
You could solve this for y and then use this one instead. But strangely, there are problems where if you do it this way, you can't get it, whereas if you calculate it this way, you can get it. We'll think about those examples. Okay? But this is what it's going to look like, and then if x is f of y, then this is equivalent to saying f prime of y squared plus 1 dy. But mainly it's this one. Now, because this one involved some algebra that felt more like a sorcery rather than math, let's try to verify this a little bit, okay? So one thing we can do is try a really simple example. Say y equals to 2x, and a and b are 0 to 1. So we want these two, this length, okay? How would you find that length? Well, if you plug in 1 here, we know that this point is 1, 2. And we know the distance between 2 points is square root of 1 minus 0 squared plus 2 minus 0 squared. It's a distance formula, right? 1 minus a. This is 0, 0, so 1 minus 0, 2 minus 0, square root. That gives you square root of 5. So I already know that the arc length is square root of 5. And let's see what this would give us. Okay? The arc length in this case, the formula would be dx. X goes from 0 to 1, so we go from 0 to 1, square root of 1 plus. This is our f of x, right? So what's the derivative? 2. And it's f prime squared, right? Then you have dx. That's going to be 0 to 1 of square root of 5 dx, whose integral is square root of 5x, and you plug in 1 and 0. Yeah, indeed, it agrees. Okay. So that's one way to verify it. However, let me give you a second idea of why this formula should hold. And this is a completely different viewpoint coming from physics. So let me ask you some physics questions. Suppose you have a moving particle and its position vector is given. If you differentiate the position, what do you get?
No velocity.
Velocity, okay? Now if you take the absolute value of the velocity, which means you're taking the magnitude of the velocity, what is that called? Speed, right? The difference between the speed and velocity is that speed is a scalar and velocity is a vector. Okay? Now, what's the antiderivative of the velocity?
Acceleration.
No, that would be the
The
derivative.
position.
Antiderivative of the velocity will be the position, okay? Or displacement if it's a definite integral. So antiderivative of the velocity is, so if you integrate velocity, you get displacement. If you integrate the speed, which is like the absolute value of v, what do you get?
Distance.
Huh?
You get distance.
You get distance. You get distance traveled. Now, why is this? Well, that's because you throw away the direction when you take the magnitude. You're only interested in how fast you go, right? If you go really, really fast, it doesn't matter which direction you're going. At least you're traveling, you're covering more distance, right? Yeah. So if I go somewhere and come back, my displacement will be 0, but I'm going somewhere and coming back. The distance will be the twice of these 2 points, right? Okay. Now, here's the idea. How does this prove us the same formula? Well, imagine that you have x comma f of x, and from A to B. And imagine that there's a moving particle here whose x and y coordinates are given by these functions. So x is like t. So at each time t between A to B, it tells you exactly where its x coordinate is, right? It's moving, so it's moving from here to there. Okay? And y coordinate is f of x, but because x is same as t, it will be like y equals to f of t. Okay? So this describes a moving point from here to there. Now, if this is the position at time t, what's the velocity? How do we get the velocity? We differentiate this, right? So this would be 1 comma f prime of t. Next question. How do you get the magnitude of a vector when given in coordinate form?
You do the Pythagorean.
Yeah, again, you do the square root of 1 squared plus f prime of t squared, right? That's your velocity. This is your, no, that's the speed. That's the magnitude of this speed. Okay. Then, if you integrate this thing from time t equals to A to B, what would you get?
You get the distance.
You get the distance traveled by this particle, which is exactly the arc length. Isn't that right? Now compare this formula with this formula. I should have really said A to B. They're exactly the same thing. Isn't that right? They're exactly the same. X is equal to t, so if you replace t by x, it's exactly the same formula. It's just that by looking at this problem using physics, it makes another reference to say why this should be the formula for the arc length. So we'll do more examples next time.